Hello everyone, this is Dr. Michael from MLR Institute of Technology. We are discussing full subtractor from the subject Digital Electronics and Computer Organization. We will see the introduction and we will look at the Boolean expression based on which how we can go for circuit minimization. We will also see the applications of the full subtractor. First of all, what do you mean by full subtractor? It is subtraction including 3 bits. If we say subtraction considering only 2 bits, it is half subtractor. So, we are taking 3 bits A, B, B in. B in stands for a borrow input. You know, whenever we perform mathematical operations, some numbers, okay, say 0, 1, 0, minus 1, 1, 0, 0 something, there are cases where we require to take borrow from the previous case, right? That is what B in represents. Now, what is the expression for full subtractor? Means it is simply A minus second variable, in this case is B, minus third variable which is B in. So, this is the expression for the full subtractor. Now, let us see how we can get this table. So, first of all, 0 minus 0 minus 0 straightforward, there is no difference, difference is 0, also there is no borrow out. So, both difference and borrow out are 0. Next case, 0 minus 0 minus 1 is actually minus 1. But how we can represent minus 1? If you take a borrow 1, then we have 1 0 minus 1. 1 0 is 2 in decimal form, minus 1. 2 minus 1 gives us 1. So, if we take a borrow 1, we are going to get a difference 1. If we take a borrow 1, we will get a difference 1. So, for 0, 0, 1, we get borrow 1, difference 1. That was the case when the result was actually minus 1. We can't represent minus 1. So, how are we going to represent minus 1? We are going to represent it as borrow 1, difference 1. So, that is what we had here. Now, let us look at the next case. 0 minus 1 minus 0 is again giving us minus 1. So, again we are supposed to have D1, B out 1. So, this is the case, D1, B out 1. Next case, 0 minus 1 minus 1, that is actually minus 2, which is actually minus 2, and minus 2 in binary form. 2 in binary form we represent 1 0, right? So, now if we take a borrow, 1 0 minus 1 0 gives us 0. So, wherever the result is actually minus 2, we are supposed to take a borrow. So, borrow will be there, but difference is actually 0. Fine. Next case, 1 minus 0 minus 0. Result is 1. So, difference is 1. We don't need to take any borrow because the result is already positive. Next, 1 minus 0 minus 1 plus 1 minus 1 will cancel. Both difference and borrow out are 0. Next case, 1 minus 1 minus 0. Again, this one will cancel. So, we will get both zeros. Next case, 1 minus 1 minus 1. Okay, these two get cancelled, and previous case we have seen minus 1, you can represent it as difference 1 and borrow out 1. So, difference 1, borrow out 1. And in this manner, we are getting the truth table for a full subtractor when the 3 inputs are A, B, B in. Obviously, the output will be difference and borrow out. Now, what we are going to do is, we are going to develop circuit diagram for this full subtractor. For that, we need to once again look at this particular truth table. To get the circuit diagram, we have to separately analyze separately analyze the difference in terms of the given inputs. And we need to separately analyze B out in terms of the given inputs. So, first, let us go for the difference D. Here, let us observe this part of the table. If you see this one, here 0, 1, 1, 0. That is what you usually get for an XOR gate. And okay, let us check for the other case also. 1, 0, 0, 1. So, based on prior experience, what we can understand is the difference is simply A XOR B XOR Bn. So, just by recollecting the truth table of an XOR gate, what one can understand is this entire part is nothing but the truth table of a 3 input XOR gate. Hence, the circuit diagram for the difference will be simply 3 input XOR gate, or we can take use of two input XOR gates. So, one is for A XOR B, and the next XOR is to perform the XOR operation between this as well as B in. The second XOR is to perform XOR between A XOR B and B in. So, that is the circuit for the difference. Now, let us look at the circuit for B out, which is borrow. There are different ways of doing this. One method is we take these values based on these inputs and then we construct the K map, perform mapping to get the minimized expression, and then based on that develop the circuit. Or there is a shortcut for this. Let us discuss the shortcut. For that, we are analyzing B out for the inputs A, B and Bn. So, you know very well that if we consider only A minus B, this is half subtractor. But if we consider 3 variables, then it becomes full subtractor. Now, when it comes to borrow, when do we have to take borrow? Whenever we are considering the subtraction case. It could be here or it could be here. Any of the case we could need a borrow. That's the reason what we are doing is we are making use of 2 half subtractors. In this case, we are making use of 2 half subtractors, and then we are taking the borrow out for the first case. We are taking out the borrow out for the second case. First case, it is the borrow out for A minus B, and the second case, it is A minus B in whole together. That is what we get here in the second case, and the first case we get here. Now, the reason for borrow could be because of this subtraction or this subtraction. So, all we are doing is we are putting an OR gate at the end, and that's how easily we could get the borrow out with minimum circuit. So, the application of the full subtractor is primarily to perform binary subtraction. And where do we need these binary subtraction? Okay, they are useful in arithmetic and logical operations inside central processing unit. So, we have seen full adder, we have seen applications. That's all for today's lecture. Thank you.